Hey everyone, and welcome back. Today we are diving into a paper that is, and I am not exaggerating, a total game changer. We're talking about teaching an AI to speak the fundamental language of the universe, the language of molecules. So what happens when a computer finally becomes fluent? Let's get into it.
I mean, just think about that for a second. What if we could design a life-saving drug or invent a revolutionary new battery? Not in 10 years, but in an afternoon. It sounds like something straight out of science fiction, right? Well, it might be a lot closer than you think. Because that's really the core promise of this incredible research we're looking at today. It's a brand new way of building an artificial intelligence that can look at a molecule and almost instantly predict exactly what it's going to do. This is a massive leap forward, so let's unpack how on earth they pulled it off. Okay, so first things first, to really get why this is so important, we have to understand the huge problem these researchers were trying to solve. You see, for decades, chemistry has been facing this massive, and I mean billion-dollar bottleneck. Think about it like this. Before you spend a ton of time and money making a new molecule in a lab, you really need to know if it's going to work. Will this thing actually fight cancer? Will it be able to store energy efficiently? Is it, toxic? To answer those questions, you have to predict its properties. And that turns out to be incredibly difficult. The authors of the paper put it perfectly right here. We literally have the instruction manual for how the universe works. It's called quantum mechanics. But the problem is, the math involved is just so ridiculously complicated that we can't solve the equations for pretty much anything more complex than the simplest molecules. So for years, scientists have had to rely on these complex simulations, like a method called DFT. And it's powerful, for sure, but it is painfully slow. We're talking 1,000 seconds, sometimes hours, for just one calculation on one molecule. But this new AI method, it does the same job in about 1/100th of a second. That's not just a little faster. That's like going from walking to teleporting. It completely changes the game. So how in the world did they get this incredible speed up? Well, they had a brilliant idea. They decided to stop looking at molecules as these super complicated 3D puzzles and instead started seeing them as tiny little social networks. Right, so the old way meant you had to calculate all these crazy complex positions and forces and angles between every single atom. It's a total computational nightmare. This new approach, it just throws all that out the window and replaces it with an idea that is just beautifully simple. They represent the molecule as something called a graph, and honestly, it's just like a social network. You've got the individual people, which are the nodes, in our case, those are the atoms, and then you have the friendships connecting them, the edges, which are just the chemical bonds. That's it. So simple, so elegant, and as it turns out, it's the perfect way for an AI to understand chemistry. Okay, so the AI sees this little social network of atoms, but how does it actually learn anything useful from that? Well, this is the fun part. It encourages a little bit of atomic gossip, and this is where the magic really happens. The specific kind of AI they built is called a message passing neural network, or MPNN for short, and the name really tells you everything you need to know about what it does. It literally lets the atoms pass messages back and forth so they can learn about the entire neighborhood they live in. The process itself is actually super intuitive. So picture this. In the beginning, each atom is all by itself. A carbon atom just knows, hey, I'm a carbon atom. Then in step 2, it sends out a little message to all its direct neighbors, its bonded friends. In step 3, it listens to the messages it gets back, and it updates its own understanding of its situation. Then you just repeat that process a few times, and just like gossip spreading through a group of friends, information starts flying across the entire molecule. And here's the kicker. After just a few rounds of this atomic gossip, every single atom has developed this rich, sophisticated understanding of its place within the entire molecular structure. The AI now has a complete picture built from the ground up by the atoms themselves. Pretty cool, right? So this all sounds amazing in theory, but the real question is, does it actually work in practice? Well, the researchers put it to the ultimate test. The results are in, and folks, they are spectacular. So what they did was they took a standard, very well-respected data set in the chemistry world called QM9. It's got about 134,000 different small molecules in it, and the goal was to predict 13 different properties for every single one. Things like its energy, its size, its stability, the really important stuff. Now, to know if the AI actually passed this test, you need to know this term, chemical accuracy. This is the gold standard. It's basically a level of precision that chemists all agree on that says, hey, if your prediction is this good, we can actually trust it and use it in a real lab to make real things. It's the benchmark that really matters. And just look at these numbers. For these charts, lower is better. And the new MPNN AI isn't just a little bit better, it's blowing the old methods out of the water. Take a look at dipole moment here. The error dropped by more than a factor of 10. Across the board, for the really critical properties that tell you how a molecule is going to behave, we are seeing absolutely massive improvements. But here it is. This is the headline, the mic drop moment. Out of the 13 different properties they tested, their AI achieved that gold standard of chemical accuracy on 11 of them. This isn't just a small step forward. This is a breakthrough. It proves that these AI models are officially ready for the big leagues. So what we have now is an AI that's not only unbelievably fast, but also unbelievably accurate. And that's not just a cool achievement for computer scientists. This has the potential to unlock the molecular universe for all of us. So let's bring this all back to the real world for a second. Why should you and I care about this? What does having a tool like this actually let us do that we couldn't do before? Well, it means we can finally start searching for brand new molecules with a speed and a purpose that we've just never had before. Think about it. Designing a personalized drug for a patient in a matter of weeks, not years, or discovering the perfect material for a next-generation solar panel or a battery that could power a whole city. So much of chemistry has been like searching for a needle in a haystack. This AI automates that search.
What this paper really represents is a turning point. It's this powerful proof that these AI models, these message-passing neural networks, they're not some lab curiosity anymore. They are well on their way to becoming a standard, absolutely essential tool for every chemist and materials scientist on the planet.
And that leaves us with one last massive question to chew on. If we can accurately and almost instantly predict what any combination of atoms will do, what are the limits? What problems could we solve? From curing diseases to tackling climate change, so many of our biggest challenges are, at their very core, molecular problems. And we may have just found a key to solving them. The secret language of molecules is finally being translated. And believe me, the conversation is just getting started.